Happy morning, guys. Today we shall discuss some interesting topic in D block elements, that is the reduction potential. What is reduction potential? Consider an electrode dipped in its own salt solution. Let me draw it here clearly. An electrode. Here an electrode is dipped in its salt solution. An electrode is dipped in its salt solution. So what happens at the junction of the electrode and the electrolyte or and the salt solution? And a potential is developed. A potential is developed at the interface, right? So that is called the electrode potential. Right? This is an electrode. This is an electrode, and at the interface, a potential is developed by the nature of the electrode. So that is called electrode potential. Got it? That is called electrode potential. Due to this electrode potential, two things may happen. That one is oxidation, and another one is reduction. Oxidation is nothing but loss of electron, right? Loss of electron may happen, or gain of electron in the case of reduction. Gain of electrons in the case of reduction. So if the electrode is a metal has a tendency of losing the electrons, so that what may happen? Oxidation may happen, right? If the electrode is a non-metal, if the electrode is a non-metal, it has a tendency to gain electrons. So here what happens? Reduction may happen, right? So the tendency of the electrolyte, whether it undergo reduction or not, whether it undergo oxidation or not, is calibrated, is standardized by a potential, by the set of values called reduction potential. In the name of reduction potential, that is, reduction potential values will decide the values of reduction potential of this reduction potential will decide whether it will undergo reduction or not, right? Okay. These values may be either positive or negative, right? Okay, this is reduction potential. Reduction potential is the potential developed by the electrode at the interface of its salt solution or electrolyte. That reduction potential value may be positive or negative based on the electrolyte, right? Okay, now let us discuss about the reduction potential in D block elements. Reduction potential in D block elements, right? So here, lithium has a least electronegative value, least reduction potential, least reduction potential. Let us denote as reduction potential value. That is negative value. That is negative value. And fluorine has a most high reduction potential value. That is a positive value, right? And hydrogen is zero. Hydrogen has zero reduction potential value, right? So here, what does it means? Lithium is a metal, right? So metal has a tendency to get oxidized. Metals are electropositive in nature. Electropositive in the nature means they have the tendency to lose electron easily, right? So that it helps in reduction. That is, it helps in reduction. Itself gets oxidized, right? Metals lose electrons. Metals lose electrons. So what happens? Itself, the metal itself gets oxidized and reduce another or reduce its counterpart. Reduce its counterpart. So let me explain with an example. Right. Let us take lithium. when it is treated with H plus ion, right? So the lithium has the most negative value and the hydrogen has zero value. When comparing these two, hydrogen has the highest value of reduction potential. So the thing which will have the highest value of reduction potential will undergo reduction. The thing which will have the highest value of reduction potential will undergo reduction, right? Here lithium has a least value, so what happened, it will oxidize, it itself get oxidized and helps in the reduction of this hydrogen. So let me complete the equation here. Li plus H plus gives H2, it liberates hydrogen, or practically Li plus HCl gives H2, it liberates hydrogen. So what happens here? The hydrogen gets reduced here. The hydrogen gets reduced here. The oxidation state of H plus is plus 1 here. The oxidation state of H2 is 0 here. So reduction, that is reducing the number of oxygen states, so reduction takes place. Right, reduction has takes place here. Now let us think about another thing. So what we got from this slide, actually lithium least electronegative, hydrogen 0, and fluorine most positive electronegative value. Least electronegative value means it reduces reduces its counterpart reduces its counterpart and itself gets oxidized So positive value means what? The opposite will happen, right? And here let us compare the hydrogen here. So if the value is positive, it helps in reduction. Let us take one more example. Copper plus H plus. The value of copper is plus 0.34. The value of hydrogen is 0. What happens will here? Either copper can reduce hydrogen here. No, because copper will be reduced because copper is having the higher reduction potential value than the hydrogen. So the reaction will not take place. The reaction will not take place. Right? Got it? So let me make it in a nutshell. That is higher RP value, that is higher reduction potential value does not displace hydrogen or H plus ion, right? Lower reduction potential value can displace hydrogen ion, displace H plus ion, right? So let me give one more example here. We know that metals plus acid liberates hydrogen. We will read it in our 10th standard itself, right? So lithium plus HCl gives H2. Whether copper plus HCl gives H2? No, not possible. This is also a metal, but this metal will does not liberate hydrogen because of what? Because it is having the higher electrode potential than the hydrogen, higher reduction potential. So copper has higher reduction potential than the hydrogen. So copper does not reduces hydrogen, right? Is it clear? Take a screenshot. Take a screenshot. So in 3D series, what are the elements present in the 3D series? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So atomic number 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Right. So we understood that the things which are having positive standard action potential will not displace hydrogen. Here in this 3D series, the copper is the only thing exception. Will have the positive positive standard electrode potential value, right? So among the 3D series, copper only will not displace hydrogen from its acid. Is that clear? This is in 3D series. And there are much more things and other things. Let us have a look. All 3D metals have a negative reduction potential except copper. Remember this most important. That is, copper has a reduction potential of plus 0.34 volt. Right? Hydrogen 0. Got it? So here lithium has a negative lowest reduction potential and hydrogen has 0, and these metals, that is copper, mercury, gold, platinum, palladium and silver too. These metals are having the positive reduction potential value. So these metal does not evolve hydrogen from acidic solution. Right? These metals does not evolve hydrogen from acidic solution. Is that clear? So by using this value, we can find out that which metals can evolve hydrogen from acidic solutions. So these metals will not evolve hydrogen from the acidic solution because of the reason they are having higher reduction potential value than the hydrogen, right? Yes, these metals will not dissolve in acid. These metals will not dissolve in acid. The answer is the same, na? That is Cu. These things will have, these all the things will have what? Higher reduction potential than H plus ion. So what is an acid? Acid contains H plus ion, right? Acid is the thing which can instantly gives H plus ion. If the metals which dissolves in the acid is they are having the lower standard electrode potential than the acid, then it will displace the hydrogen. But these are all having the positive value and hydrogen is 0. So they are having higher value than the hydrogen so that it cannot displace. So remember the element, the element with lower RP value, lower reduction RP value shall displace, shall displace element with higher RP value, but the reverse cannot take place. The reverse cannot take place. Right? Clear? Make a note. Make a note. That is, let us make the order here. Let us make lithium here and hydrogen here and copper here and finally fluorine here. So the displacements can take place in such a way, that is, this can displace this, but this cannot displace this. Is it clear? Right? That is why these elements, that is copper, mercury, gold, palladium, platinum and silver too, does not dissolve in acid. Right. This is the electrochemical series. This is a list, standardized list of the standard reduction potential of all elements. Of the standard reduction potential of all elements. Now, look here. Um, Here, the value of hydrogen. The value of hydrogen is here 0. Right? The value of hydrogen is here is 0. This is most important. Here, this is the redox table. The potential under standard conditions. I'll explain this one. What is standard conditions? The point we have to get from here is this. This is also the reactivity series 2 or reduction series 2. Right. Here we can understand that this is a H plus one. Right. As I told in the previous slide, look here. It can the metal which is in the highest place can displace the thing which is in the lowest place, and the reverse cannot take place. Right. Here, this is the reactivity series. Look here. In the reactions, the metals which are present in the upper side, the metals which are present in the upper side can displace a metal in the lower. For example, lithium can displace aluminium, but aluminium cannot displace lithium. So this is called reactivity. The reactivity is decided by the RP, the reduction potential. The reactivity shall be decided by the RP, right? The reduction potential. Same thing. That is, iron can displace lead, but lead cannot displace iron, right? Potassium can displace magnesium, but magnesium cannot displace potassium, right? So like that, these metals which are on the higher side, these all the metals can displace hydrogen from acids, but these metals cannot displace hydrogen from acids. Okay, so let us have some clarity regarding the oxidizing agents, reducing agents. Okay, let us explain this with an example. Consider this reaction. CuO plus H2 gives Cu plus H2O. Right. Here the oxidation state of copper is plus 2. Here it is 0. Here the oxidation state of hydrogen is 0. And here it has been plus 1. So what happened? The oxidation state decreases. So what happens here? Reduction takes place. And here the oxidation state increases. The oxidation takes place. So here the hydrogen is oxidized, right? The hydrogen is oxidized here, right? And here the copper is reduced. So what happens here? The hydrogen helps the process of reduction. Hydrogen itself helps itself oxidize and helps in the process of reduction. So it is called as a reducing agent here. This is called as a reducing agent. Reducing agent, right? And the copper itself gets reduced here. It helps in oxidation here in this process. So it can be called as oxidizing agent. Oxidizing agent because it helps oxidation, right? So simply oxidizing agent. Oxidizing agent means what? Which is getting reduced. Here hydrogen is getting reduced. That can be considered as oxidizing agent. The oxidizing agent getting reduced itself, right? Like that, the reducing agent. Who's the reducing agent? Which get oxidized. Which gets oxidized, right? So remember, oxidizing agent always have the tendency to getting reduced by itself, right? So listen here. So here the oxidizing agent mentioned here. Here, the oxidizing agents in the sense what we have to understand itself getting reduced. That is the oxidizing agent they will be getting reduced. The oxidizing agents they will be getting reduced, right? And the reducing agent they will be getting oxidized. They will be getting oxidized. Oxidized, right? Is that clear? So oxidation, reduction, reducing agent, oxidation agent, right? Now, the weakest oxidizing agent, strongest reducing agent, the strength of oxidizing agent, the strength of reducing agents, right? So listen here, weakest oxidizing agents, it means the tendency of reducing the counterpart is less. As we told earlier, listen here, higher the reduction potential, the more easily the substance is reduced. Higher the reduction potential, that is, if the if the E naught value is highly positive, what it shows? It can get easily reduced. It can get easily reduced, right? And the opposite side, if it is more negative, it can be easily oxidized. If it is more negative, it can be easily oxidized, right? So this is a table of standard electrode potentials, and by using this, we can find out the reactivity of elements. Next, so this is the answer we had. As a reduction potential value is greater than the value of H plus, they cannot liberate acid in a solution, and hence they cannot form a soluble salt. Right. This is the answer we discussed earlier. Then we can discuss about magnetic property. What do you mean by magnetic property? Yeah. When a substance, when a substance is subjected to magnetic field. When a substance is subjected to magnetic field, there are two possibilities. That is, one, it can align or attracted towards a magnetic field, or it will repel towards a magnetic field. Two things can happen, right? If a thing is aligned towards a magnetic field or attracted towards a magnetic field, that is called paramagnetic material. Paramagnetic. If it is repelled, that is called diamagnetic. Diamagnetic. Right. We can remember this word by using the Hindi word called pyar. Pyar mohabbat. Right. Paramagnetic. That will loves. Pyar means love. What it loves? It loves a magnetic field. It loves a magnetic field. Right. So these are the properties of the magnetic. These are the magnetic properties of the materials. Right. It can either attract or it can either repel. So if it is attracted, it is called para, and it is deflected, it is called a diamagnetic, right? So how does this property comes to an element? So this paramagnetic and diamagnetic, this property comes to the element by the arrangement of electrons, paramagnetic, diamagnetic. So paramagnetic means you have to understand the element should has unpaired electrons, unpaired, para, unpaired. Dia means what? Two. Di, two. Diamagnetic means paired. Paired. Here, let us consider the d orbital here. This is for just an example. So, paramagnetic in the sense there should be unpaired electrons. Unpaired electrons. Like this, there should be unpaired electrons. Either any one of paired and others may be unpaired. Diamagnetic in sense, all the electrons will be paired. All the electrons will be paired here. So there is no unpaired electrons. So this exhibits paramagnetic, this exhibits diamagnetic. So this is about the magnetic field. And yes, paramagnetic means a substance attracted towards a magnetic field and it requires the presence of unpaired electrons. Diamagnetic means a substance repelled by the magnetic field and it requires absence of unpaired electrons. There must not be unpaired electrons there. And the diamagnetic or paramagnetic can be calculated by using the formula. Mu is equal to 4 root of 4s into s plus 1 where s is equal to n by 2. And that will give rise to another formula root of n into n plus 2. So this is an important formula what we are using, right? In your level, in senior secondary level, we can use this formula. So n is equal to n plus 2, right? Okay, n is nothing but the number of electrons. Let us consider a few examples here. Let us take scandium. Scandium atomic number is 21. So we can write argon 18 and 3d 1, 4 is 2, right? So here 3d1, 3d1 in the sense if you draw the d orbital and the s orbital, this is the s orbital and this is 4s orbital, this is 3d orbital. So 4s2, the s electron will be filled before the d electron because the energy gap is very low. So another one electron is here, na? So one electron will be like this. So the number of unpaired electrons is here 1. What is the formula to calculate the magnetic moment? That is root of n into n plus 2, right? So that is equal to, in the case of scandium, root of 1 into 1 plus 2. So that is equal to root of 2. Sorry, root of, it's not root of 3. So it's nothing but 2 plus 1, 3, 3 into 1, that is the root of 3. So it will be approximately equal to 1 point something. It will be approximately equal to 1 point something, right? And the next element is titanium 22. So it will be 3d2 4s2. So the number of unpaired electrons will be 2. So the value will be root of 2 into 2 plus 2. N into n plus 2. No? So that is equal to 4 into 2, 8. The value will be 8 and that is approximately equal to 2 points. That is approximately equal to 2 points. Then scandium, titanium, vanadium. If we go on, we can observe a thing. That is, we can observe a thing. What is the n here in scandium? N is equal to 1. What is the n here in titanium? N is equal to 2. What is the value here? 1.2 points. So it is directly related. That is, if the number of unpaired electrons is 1, the magnetic moment value will be 1 point something. If the number of electron is 2, if you calculate the magnetic moment will be 2 point something. So like that 3, the magnetic moment will be 3 point something. So this is a short trick, important. Remember, note it down. So the mu value, that is the magnetic moment value, is approximately equal to the number of unpaired electron. The number of unpaired electron. Got it? The number of unpaired. If in a problem the value of magnetic moment has given us 3, and they are asked whether the thing is paramagnetic or diamagnetic. So we can easily ascertain the number of unpaired electrons is 3. So it will be paramagnetic, right? The number of unpaired electrons is 3. If the value is 3, right? Okay, and then only the paramagnetic compounds will have this magnetic moment value. So this is a short trick to find out the magnetic moment value from the number of unpaired electrons or the number of electrons from the magnetic moment value, right? Next, color of the compounds. Regarding the color of the compounds, you have to understand how, while talking about the d block elements, this is a particular property of d block elements. D block elements, that is the color of the compounds. Because of the reason, only one reason, unpaired electrons, due to the presence of unpaired electrons, right? So listen here, K2Cr2O7, what is this? Potassium dichromate, right? Potassium dichromate. So what is the color here? That will be orange in color. That will be orange in color. And due to the, what is this? Due to the presence of a d block element, chromium. The chromium is in +6 oxidation state here. Right, like that in KMnO4. What is the color of KMnO4? Purple. Right, the color of KMnO4 purple. So due to the presence of M1 here, the oxidation state of M1 is +7 here. And so the color is mainly due to the incomplete N-1 subshell. What is the reason first? Note it down. Incomplete N-1 d subshell. N-1 d subshell. That is incomplete d orbital. Incomplete d orbital. Right. First point, we have to remember incomplete d orbitals. Incomplete d orbitals means there will be vacant space in d orbital. Right, there will be vacant space in d orbital. So this is d orbital. Some electrons may be filled and some space over there. So I think we had seen already the examples of scandium, Sc21. So what is this? 4s2, 3d1. So only one electron is filled here. So these remaining spaces are incomplete, vacant. So this is one of the reasons for the color of the compound. Right. Let me write it in the same slide so that you can easily note down. So reasons for color of the compounds. First one I said that incomplete incomplete d orbitals, right? And second thing we have to understand splitting of d orbitals. Splitting of d orbitals. Splitting of d orbitals in the sense what happens? D orbitals, we know that there are 5 orbitals. 1, 2, 3, 4, 5, right? So what happens when the electron approaches, it splits into 2 levels. So this is called degenerate orbitals. Degenerate orbitals. Degenerate in the sense, what does it mean? Equal energy. Equal energy. When the energy is higher, it breaks down here and it splits into 2. That is triply degenerate. T2G means triply degenerate and EG means doubly degenerate. The T2G and EG doubly degenerate. So in the case of octahedral complexes, octahedral means octahedral complexes, this will be T2G, EG, T2G in down and EG in top. In the case of tetrahedral complexes, EG will be in down. EG, doubly degenerate will be in down and T2G will be in the top. Right. What happens here? The d orbital splits down when the electron approaches and this splitting gives space for the electron to move. So what happens when an electron present in the lower energy level like this, when some amount of energy it gets, it excites to the higher energy level by absorbing energy. But after some time, it will return back to the lower energy level by emitting that energy, right? So this emitting energy, when it falls in the visible region, VR, when it falls in the visible region, colors are produced. When it's falls in the visible region, colors are produced. So this movement of electron from one part of d orbital to another part of d orbital is called dd transition. It's called dd transition. This is called a dd transition. So because of this dd transition, colors are observed. Let me explain one more time. When the electron approaches with higher energy, the d orbitals, that is, here, let me draw here. The d orbitals 5. The d orbitals get splitted. This is called degenerate place. It gets splitted into two groups. That is 3 in one place and 2 in another place. These are the boxes here. This is called a T2G or triply degenerate. This is called EG or doubly degenerate. Right? When the electrons present in the lower energy state, it absorbs a photon. It gets rises to the higher energy level, and after some time, when it returns back to the lower energy level, it emits the energy absorbed. This energy level, when it falls on the VR region, that is the visible region, it shows us a color, right? It shows us a color. Right, the second point is simply we can write this incomplete orbitals. The first point, second point is DD transition. The second point is DD transition, right? So the reason for the color of the compounds is unpaired electrons. That is right. Unpaired electrons. And second one, splitting of d orbitals. Splitting of d orbitals. And DD transition. DD transition. Right. So this is the reason for the color. Okay. Then the colors are of different type. Na? So what is the color depends on? So the colors, let me have a look over here. Let you have a look over there. Reason for our colored compounds, many transition metal compounds are colored due to incomplete filled Dn-1 D subshell. That is 3D, 4D, 5D. Right. So that is due to the splitting in the isolated gaseous atom, or ion. The 5D orbitals are divided into two categories, Eg and T2G. Eg means you know that doubly degenerate. Doubly degenerate. This is called a triply degenerate. The word degenerate means equal energy. These are called degenerate orbitals. Degenerate orbitals. That means equal energy. Here all the 5 orbitals having the equal energy. Actually this is dxy, dyz, dxz. It gets splitted, it gets divided into two. Then electron can easily transfer from one level to another level by absorbing energy, and color arises when it releases energy after coming into the ground state. As I said earlier, look at this diagram. Here what happens here, if an electron presents here, it absorbs some energy and reaches here. It absorbs some energy and stays here for some time. After some time, comes back. At the time, it releases the absorbed energy, and this energy, if it is fallen in the visible region, if it falls on the visible region, and that produces a color. That is why the compounds having unpaired electrons are colored. Right. Next, let us think about the reason for color, because there are different colors in presence of unpaired electrons one, and nature of the ligand and geometry, ligand and complex. So I'll give a simple example. We will have a detailed thing while we are studying the coordination compounds. Ligand in the sense the thing which approaches another element. For example, if Cn is coming to make bond with what is that? Iron means the Cn is a ligand. So this is a metal atom. This may not be a metal atom. So that is a ligand. And geometry means we know that the structure of complex. Structure of complex means like this. So the shape. So this is the geometry. This is the geometry. This is a square planar, right? This is the geometry of the complex, right? And most importantly, we have to understand when the d orbital is completely filled, the compound is colorless. Completely filled, the compound is color. That is why That is why zinc is colorless, because what is the electronic configuration? 3d10 4s2. The zinc is colorless. That is why, because of the reason of it is completely filled. Then, so VO2 plus. So the color of this compound is yellow, and CrO4 2 minus. The color is deep yellow. M1O4 minus, the color is purple. CrO2 7 2 minus, the color is all. The color is orange. So these are all due to the charge transfer phenomena. Charge transfer phenomena. What is charge transfer phenomena? That is the electrons transfer their charges to the ligands transfer their charges to the central metal atoms. Need not to get into deeper. You just remember, due to the presence of unpaired electrons, these are all colored. Uh, that is okay for you, because if we talk about the charge transfer phenomena, we have to know about the metals, ligands, and everything related to coordination compounds. So this can be explained while we are discussing about coordination compounds, right? So simply at this time we can understand that the ligands transfers its charge to the CM atoms, central metal atoms. So that is enough for this time. So simply we can remember presence of unpaired electrons, and due to the movement of unpaired electrons from one place to another, and while returning they are emitting the energy, due to that the color is produced, right? Then let us go for alloys. Alloys means you know that alloy wheel, that is mixture of metals. Whether all metals can be mixed together? No. Let me explain this. So alloy is nothing but the mixture of element, right? So here brass. Brass means, what is brass? It looks like what is that? Gold. Na? That is copper plus zinc put together. That is called brass, right? And bronze. Bronze means copper and tin put together mixed means, that is called bronze. This is bronze, this is copper, this is brass, and this is bronze, right? Mixture of element. And gunmetal or bell metal or stainless steel. Gunmetal is nothing but, we can remember simply that this put together is gunmetal, gun or bell metal. So what do you mean Cu plus Zn plus Sn, right? That is gunmetal or bell metal. Stainless steel means, that is chromium plus nickel plus iron, and some amount of carbon is also added. The carbon is added for strengthening, for strength. Carbon is added for strength, right?